For 5.2, we are going to talk about a very specific type of probability distribution. Think of this as the unicorn, or maybe we should call it the biacorn. Maybe it's a binomial probability distribution. Binomial means that there are only two outcomes, heads or tails is a binomial distribution. Rolling a dice would not be binomial because when you roll a dice, there are 6 different outcomes, 1, 2, 3, 4, 5, 6. And so in a binomial probability distribution, we only have 2 outcomes. Anytime we talk about the probability of success, I try to highlight that in green. And anytime we talk about the probability of failure, I try to highlight that in red. P is the value that we use to represent the probability of success, and Q is the variable we use to represent the probability of failure. If you know one, you immediately know the other because guess what? They're complements. If there's a 30% chance of snow, you immediately know that there's a 70% chance of it not snowing. And it's also important to notice that these trials are independent, which means that it doesn't matter whether or not you have a condition, the probabilities are the same. Remember, we talked about conditional probabilities and things being independent. The coin doesn't remember what its last flip was. So the probability of flipping a coin is always 50-50. It's independent of its past events. We're going to look at this example. And this is a long example. And the example, the end result of this is we are going to derive this formula. This is how you calculate probabilities with a binomial probability distribution. And so there are some components that we need to identify. So first, this is a familiar character, NCR. This is the formula for combination pizza. Remember combination pizza, where you had so many items and order didn't matter, the sequence didn't matter? That's that formula. So it appears here. We also have P to the R power. In other words, the probability of success to the power of the number of successes, and Q to the N minus R power, which is the probability of failure to the power of the number of failures. And so we're going to derive these 3 components. We're going to show you where they come from. And we're going to develop that by looking at this lengthy example. This is the situation that we're going to use to develop the formula. So we have a 3-question multiple choice test. 1, 2, 3. Okay, 3 questions. Each question has 4 possible outcomes, one of which is correct. So the probability of success on the first question would be 1 out of 4. And the probability of failure on the first question would be 3 out of 4. So we know P is 1 out of 4, and we know Q is 3 out of 4. Now there are 3 questions here. So really quick, if question number 1, question number 2, question number 3. So what would be the probability of getting question number 1 correct, question number 2 incorrect, and question number 3 correct? What would this probability be? Well, you would say the probability of getting the first question correct is 1 out of 4. The probability of getting the second question incorrect would be 3 out of 4. And the probability of getting the third question correct would be 1 out of 4. And so you would multiply these together. And you would get 1 out of 4 to the second power times 3 out of 4 to the first power. And the second power and the first power are not a coincidence. How many correct answers do we have in this situation? We have 2 correct answers, which is why there's a 2 as an exponent on P. The probability of success to the power of the number of successes. How many do we have that are incorrect? Just 1. And again, that is the exponent on the probability of failure. How many do we get incorrect? 1. So that is Q to the first power. So this is the probability of this specific example. So this is how you would calculate for a specific value, a very specific value. And that's what we do in here. So here are P's. P is 1/4, 25%. Here is Q, 3/4, 75%. And we would like to know, what is the probability of getting exactly 2 questions correct? Exactly 2. So in the sample space, here are all the variations you can have. And here are the examples where we have 2 questions correct. Notice this one, all 3 are correct, so we don't want that. Here we only get 1 correct, 1 correct, 1 correct. And here we have 0 correct. So this is 0 correct. This is 1 correct. These are 2 correct. And this would be all 3 correct. Okay. And we want to know, what is the probability of getting exactly 2 correct? So this becomes our event space. These are the events that satisfy the condition of getting 2 correct. So what's the probability of each one of these? So if we take just this first example, or actually let's take this example right here. This is the calculation we just did. First one's correct, second one's wrong, third one's correct. We just did that up here. First one's right, second one's wrong, third one's correct. And so we know what this probability is. It's right here. 1/4 to the second, 3/4 to the first. So this probability for this event right here, and everything that I just talked to you about, is actually displayed right here. 1/4 to the second, 3/4 to the first. That is the probability. This is the probability of getting the first one right, the second one wrong, and the third one right. Now that probability is the same for the other 2 situations. 1/4 to the second and 3/4 to the first. So if you take all 3, this probability, this probability, and this probability, they are all 1/4 to the second, 3/4 to the first. Now, how many of these do we have? We have 1, 2, 3 of them. So we could just say that this is 3 times 1/4 to the second, 3/4 to the first. And if you calculate it out, you actually get this value, 14.1%. So there is a 14.1% chance that you would get exactly 2 questions correct. And we sort of shown it here. Now, what if we changed it around? What if we wanted to know, instead of 2 questions, what's the probability of getting 3 questions correct, or 1 question correct, or 0 questions correct? What is the probability distribution for all the outcomes? Well, here they are, using the exact same procedures we used earlier for the 2 questions correct, right? 1/4 to the second, 3/4 to the first, 3 times that. We can also show the same calculations for getting 0 correct, 1 correct, or 3 correct. This is the entire probability distribution for a 3-question multiple choice test. And now we make the generalization. So in our situation, P is equal to 1/4. Q is equal to 3/4. This comes from the individual outcomes for each event. The number of trials that we do, the number of questions that we have, is equal to 3. And R, the number that we want correct, is this value. It's either 0 or 1 or 2 or 3. So if you want to find the probability of getting all 3 correct using this formula, it would be 3C3 times 1/4 to the 3rd power times 3/4 to the 0 power for all 3 being correct. So here's the spreadsheet. And notice up here, we have the number of trials, N. This is the number of questions on the quiz, okay? This is R, the number of successes that you're looking for. And this is the probability of success. In our case, this was 0.25. It was 25%. We don't need to type in Q, because once we know P, we automatically know Q because of the complement. Here is the calculation of NCR. And notice we use the combination formula from last chapter. Remember 4.4 when we looked at counting techniques and the formulas for permutation and combination? Boop, there it is. There's the combination formula. We also calculate P to the R power, the probability of success to the power of the number of successes, and Q to the N minus R, the probability of failure to the power of the number of failures. So if I have 5 questions on my test, and there are 4 possible outcomes for each question, and I want to know what is the probability of getting exactly 2 correct, then NCR is 10. The probability of success to the power of successes is this. The probability of failure to the power of failures is this. And you multiply those all together, and this is your probability. There is a 26% chance that if you have 5 questions on a multiple choice quiz, in each question, you have a 1 out of 4 chance getting it right. There's a 26% chance that you would get exactly 2 of those questions right. What about 3 questions right? Well, you got an 8% chance of getting 3 questions right. What about 4 questions right? A 1% chance. What about getting all 5? What is the probability that if you guess randomly on 5 questions, not very high, less than 1%? The spreadsheet actually goes through and does this calculation for you, but you've got to know P, Q, N, and R. 1% of the people in the world have green eyes, 1%. So this means my probability of success is 0.01. That's 1%. The probability of failure would be 0.99. Let's say that we have a group of 20 people. So that means N is equal to 20. Now we need to know, what is R? How many of these 20 people do we want to find the probability of that they have green eyes? Okay, so in the first situation here, we want to find the probability that no one has green eyes. So that would mean R equals 0. P is equal to 0.01. Q is equal to 0.99. N is equal to 20. R is equal to 0. We're going to take these values and we're going to plug them into the formula that we have. So here's NCR. Here is the probability of success to the power of the number of successes, which would be 0. And this is the probability of failure to the power of the number of failures. You multiply these 3 things, blue times green times red, and you get your answer. There's an 81.8% chance that no one in the group will have green eyes. So in our Google Sheet, we're going to say the number of trials is 20. Boop, boop. Okay. The probability of success is 0.01, 1%. And we want to find what is the probability that no one has green eyes. So R is 0. Ready? Here we go. 3, 2, 1, boom. NCR is 1. So we show you all the individual components. The probability of success to the number of successes is 1. The probability of failure to the number of failures is 0.81. You multiply those 3 together and you get this value, 81.7907, or 81.8% chance. There's an 81% chance that in a group of 20 people, no one will have green eyes, if it's assumed that 1% of the population has green eyes. Now, this is a very non-intuitive process. It's very hard for you to use your gut to sort of figure out what the answer is going to be. So you want to rely on these calculations. Let's go down to the next one. What is the probability that 9 people have green eyes? So in a group of 20 people, what is the probability that 9 people have green eyes? So in this case, R is equal to 9. Everything else stays the same. The number of people we have in the group is 20. The probability of success is still 0.01. The only thing that changes is our R value. So we're going to change this to a 9. And look, it's not actually 0. Let me add some decimals. There we go. Look at that. That's your probability. But it's not 0, right? I'm telling you there's a chance. It's not 0. If we say it's 0, then that means it will never, ever, 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 ever happen. This says there's a chance. It's a small chance, but it's still a chance. We just showed you how to do this step by step. You find N, R, and P. We showed you the components. Here's NCR, here's P to the R, here's Q to the N minus R. These are the three important components that we developed back up in here with this formula from our example. And here is those three components multiplied together to give you the final probability. But there is a shortcut. Google Sheets has a built-in formula specifically for binomial distributions. And that formula is called binomial distribution. And there are four inputs. Input number one is R. Input number two is N. R would be the event space. N would be the sample space, right? The number that you want to meet your condition and the total number. P is the probability of success. We know what that is. And then finally, this last variable is whether or not you want this probability to be cumulative. And by cumulative, what we mean is, do you want it to be exactly 9 people with green eyes, or do you want 9 or less? 9, 8, 7, 6, 5, 4, 3, 2, 1, all added up. So in this particular case, when we're talking about the 9 people with green eyes, we want exactly 9. R is exactly 9. So we do not want this to be cumulative. So we set that to false. Okay. Now, if you take a look at the next example, it says find the probability that at most 3 people have green eyes. At most 3. So that means the probability of 0 plus the probability of 1 plus the probability of 2 plus probability of 3. We've got to calculate each one of those and add them all up. You could go into your spreadsheet and you could type in a 0. So you take the number for 0, add it to the number for 1, 16, add it to the number for 2, 1.5, add it to number for 3, and that's what we show you here. You would take these 4 probabilities and you would add them all up to find the probability that 3 or fewer people had green eyes. Or you could use the cumulative and change that from false to true. Now what this will calculate is not only the number that have 3 green eyes, but it will add up all of the values less than 3. So the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0. That is the cumulative. And it's really handy. So that way you don't have to do all of these individually. It just adds them all up together. So notice on the spreadsheet, this is the exact probability for an exact event. And this is the probability cumulative. Everything up to and including that specific event. A poll is given showing that 65% are in favor of a new building. That is our probability of success, 65%. So I'm going to go over to my spreadsheet really quick, and I'm just going to clear out these values. And we know that the probability of success is 0.65. So let's put that in. So there's my probability of success. I also know that my probability of failure is 35%, right? Because the complement. If 10 people are chosen at random, so this is my sample space, 10 people, right? The number of trials, I'll put in 10. What is the probability that exactly 7 of them favor the new building project? So the number of successes, the number of people that favor the new building project is 7. So my value for R is 7. Now the answer is sitting right down here, but let's go through all the components. This is 10 combination 7, 10 CR. There's 120. That's that value. This is 0.65 to the 7th power. And this is 0.35 to the 3rd power. We take each of those individual components and multiply them together, and there is our answer. And there we go. We got it correct.